Well, good morning, ladies and gentlemen. So today's topic, we're going to finish off chapter 4, which is the energy balance, right to the end of chapter 4. And then we're going to begin chapter 5, which is the second law of thermodynamics. That's the plan for today. So let's go over the specifics. We're going to finish off chapter 4 by looking at cyclic devices. Cyclic devices are devices for which over the process, all change in properties are zero. So the device works in a cycle, delta T, delta E, delta U, delta P. All the change in properties end up being zero over the cycle. That's the definition of a cycle. No change in any properties over the cyclic process. So we're going to look at 3 different devices that operate in a cycle. A heat engine. A heat engine produces work. A heat engine receives heat and produces a certain amount of work. We're going to look at heat pumps and refrigerators. Heat pumps and refrigerators are responsible for transferring heat from a cold place to a hot place. Think of the air conditioning device in your car or the air conditioner in your house or office. Those are heat pumps or refrigerators. Or think of the refrigerator in your kitchen. The kitchen is responsible for transferring heat from the icebox or the refrigerator compartment to the room. So refrigeration devices, heat pumps, are responsible for transferring heat from a cold place into a hot place. And because nature wants to do the opposite, heat naturally flows from hot to cold, you have to provide a certain amount of work to move heat from a cold place to a hot place. So we're going to look at 3 different cyclic devices and then finish off with an example. And then we're going to move on to chapter 5. So chapter 5 is the second law of thermodynamics. Chapter 5, second law of thermodynamics. We're going to start off with a little discussion about why we need the second law of thermodynamics. That's our motivation. We have the energy balance. Aren't we done? Well, the answer is no. Then we're going to look at terminology. For the second law of thermodynamics, there's a certain set of concepts that you need to be familiar with when we discuss the second law of thermodynamics. Then we're going to go over 2 statements. And these statements are pictures, if you like. So for the inner artist in you, this is your chance to indulge in some pictures or drawings or sketches, no math at this point today with respect to the second law of thermodynamics. So we're going to look at 2 pictorial representations or statements of the second law of thermodynamics. One is the Clausius statement, and the other is the Kelvin-Planck statement of the second law of thermodynamics. They're going to be pictures, not equations. Don't worry. We will be developing these pictures and applying various mathematical concepts to arrive at an equation statement, a mathematical statement of the second law. We'll be doing that next week. But for this week, we're going to start off with a pictorial representation of the second law of thermodynamics. Okay? So we have quite a bit of material here. Most of it's conceptual to go over today. All right, let's look at cyclic devices here. So what do we mean by a cyclic device? What we mean by a cyclic device is the change in any property is equal to 0 over the process. So change in any property equals 0 over the cyclic process. So clearly a graphical representation of this, let's say I have property 1 and property 2, could be pressure, volume, temperature, volume, internal energy, temperature, could be anything. So the system starts off at a particular state, wanders over some process, and ends up back at the original state, okay? There could be some intermediate states. So this is State 1 is the original state. You could end up with at an intermediate state, state 2, intermediate state, state 3, and then you go back to state 1. So the change in any property from 1 to 2, back to 1 is going to be equal to 0, okay? Now, another way of saying this is for a device that operates over time. You can say that the rate of change in all properties. Another way of saying a cyclic device is the rate of change, property dot, or if you like, d property dt, no change in any properties over time. You could say that as well. Okay? No change in properties over a cycle, over a cyclic process, or no change in property values with respect to time. These are both ways of referring to a cyclic device. An example here might be a device. See the circular arrow there? A device working in a cycle. This device receives a certain amount of heat and produces a certain amount of work. So this heat might be a heat input, Q dot. Receive a certain amount of heat, produce a certain amount of work, and reject or output a certain amount of heat. This would be a heat engine. A heat engine is a device that takes heat and produces work. So this cyclic device might be referred to as a heat engine, HE. Takes some heat, produces some work, and whatever is left over spits out as some rejected heat, Q dot out. So that's an example of a rate-based application of a cyclic device, okay? All right, let's go over 3 different kinds of cyclic devices. We've already talked a little bit about heat engines. Let's go over heat engine, refrigerators, and heat pumps. Now, before we do that, I want to define a new quantity. Define a new quantity. You should have an intuitive understanding of this quantity, so I don't think it's going to be a big leap. So the concept of efficiency. Let's define efficiency. Efficiency. What is efficiency? We're going to go over the 3 different devices and calculate their efficiency. So I want to introduce the concept first. So efficiency, in general, is some kind of a benefit over a cost. A benefit over a cost. Now, let's apply this to a heat engine. So what is a heat engine again? Heat engine. A heat engine takes as input, so here's my heat engine, takes as input some kind of heat, Q in, produces a certain amount of work, W, and whatever is left over, let's say this heat engine is working in a cycle. So this heat engine works in a cycle, takes a certain amount of heat, produces a certain amount of work, and whatever energy is left over rejects as Q out. Okay? By the way, if you apply the energy balance to this heat engine, so let's apply the E balance. We can get an expression for Q out. Let's see, E balance. Q minus W is equal to delta E. Now, this is a cyclic device, so we're going to apply this equation over the cycle. So write cycle for the subscript on the energy balance. We know that change in any property, energy included, is equal to 0 over any cycle. Cycle. So delta E is equal to 0. Heat and work are not properties. They're path functions. So they don't typically go to 0. In some situations they do, but in general they don't go to 0 over a cycle. Now, what's the heat addition over the cycle? Well, this device receives a certain amount of heat in, Q in, and rejects a certain amount of heat out, Q out. So that's the heat over the cycle, Q in minus Q out. And the work over the cycle is simply W. Okay? Let's take the W and put it over on the right-hand side and then flip the equation. And I get W. I tell you what, I'm going to leave this as W cycle. Just to imply, just to drive home that we're looking at a cyclic device. So I'm going to change this to W cycle. So this means that the work over the cycle is equal to Q in minus Q out. Okay? Or if you like, Q out, let's solve for Q out. Q out is equal to Q in minus W cycle. So this heat output is Q in minus the work produced over the cycle by the cyclic device, okay? That's just from the energy balance. That's just from the energy balance. Let's calculate the efficiency. Let's get the expression for the efficiency for this cyclic device. Well, the benefit for a heat engine, so in the case of the heat engine, the benefit is the work produced. The emphasis is on the work produced by the cyclic device. So the work over the cycle is the benefit. What does it take to run? What's the cost of running the heat engine? Well, heat has to be received from some source in order to produce a certain amount of work and reject a certain amount of output heat. So this guy, Q in, is the cost. This is what's actually driving the heat engine, the cyclic device. So I'm going to put Q in as my cost. So the ratio of the work produced over the cycle divided by the heat input, that's the efficiency of my heat engine. So I'm going to write that right down here. I'm going to introduce a symbol that's typically used for efficiency, eta. So write eta is equal to efficiency, which is equal to W over the cycle divided by the heat input. Put a box around this. This is for a heat engine, and this is how we define the efficiency. Efficiency for a cyclic device heat engine, okay? W cycle over Q in, benefit over cost, okay? So that's efficiency for a heat engine. Let's look at another device. Let's say instead of producing work as being the benefit, instead of producing work, we're more interested in a device which transfers heat. So let's say I have a hot place. T hot, and the cold place, T cold. Hot, cold. Now, naturally, heat flows from hot to cold. You put these two areas or spaces in thermal contact with each other, and heat's going to flow from the top to the bottom, from hot to cold. Now, if we want heat to flow the other way, if instead I want to pull heat from the cold place, so Q cold, Q hot. If instead I want to transfer heat from the cold place to the hot place, I have to do work to do it. So I have a device here, a cyclic device. And this device is going to receive a certain amount of work, W, over the cycle. Applying a certain amount of work, this device will transfer heat from the cold to the hot place. This device is called a refrigerator, R-E-F, refrigerator. Refrigerator, R-E-F. It doesn't produce work, unlike the heat engine, it transfers heat. So refrigerator transfers heat from a cold place to a hot place, but requires work to do so. Because in nature, heat flows naturally from hot to cold, not from cold to hot. So to get heat to flow up, we have to do work. This is the refrigerator that you have in your kitchen, the air conditioning system you have in your car, the refrigeration system or air conditioner you have in your house. These are all refrigeration units that require work input to transfer heat. How do we define the efficiency for this particular device? I'm not going to use eta. As for a heat engine, I'm going to use what's called a coefficient of performance. So efficiency, I'm going to call it the coefficient of performance. So COP. COP is coefficient of performance. Coefficient of performance, COP. Instead of using the symbol Greek letter eta, as we did for the heat engine, I'm going to use COP, coefficient of performance. This is a refrigerator, so I'm going to write REF. So efficiency for a refrigerator is called the coefficient of performance, and it's equal to a benefit over a cost. Remember, efficiency in general is defined as a benefit over a cost. So for a refrigerator, what's the benefit? The benefit is the heat transfer from the cold place. Q cold. That's the heat transfer from the cold place. A refrigerator is meant to cool a cold place, keep a cold place cold. So that's the benefit, Q cold. And what's the cost to run the refrigerator? It's the work input. Q cold over W. Coefficient of performance, COP. Q cold over the work. So the coefficient of performance for a refrigerator is defined equal to the heat transfer from the cold place divided by the work required to run the device, okay? If you want to put a W cycle here, that's fine. I could have put a W cycle here, but I didn't, all right? Now, before we go on, I want to say you can actually rewrite this efficiency for a device that runs continuously in time. This is the device here that runs in a cycle. So I could write this as Q cold over W, but I could also write it as Q dot cold over W dot. That would be the continuously running dE dt equals 0. Change in any property is 0 over time. For the continuously running device, Q dot cold over W dot, or Q cold over W. Okay? So let's extend the picture here. I can also write this. If it's a continuously running device, I can write this as Q dot cold, W dot, or Q dot hot. Okay? It's for a continuously running device. And we can also do this for a heat engine. Let's go back and clean up our picture for a heat engine. This could be a continuously running device. So I have Q dot in, I have W dot cycle, and I have Q dot out. So I could rewrite this expression for efficiency for a continuously running device. I can add in one more expression, W dot cycle over Q dot in. I could do this, and I'm going to, okay? Let's look at one more device here, now that we have the right frame of mind for looking at these kinds of situations. So refrigerator. The purpose of a refrigerator is to transfer heat from a cold place and shove it into a hot place. We also have what's called a heat pump. The picture is exactly the same. So we have a T hot place, cold place. This heat pump, HP. So this is a heat pump. It's operating in a cycle. Transfers some heat from a cold place, Q cold. Forces it into a hot place, Q hot, but of course requires a certain amount of work. Okay? Now for a heat pump, the emphasis is on the heat transferred to the hot place. Think of the heat pump in your house. In the winter, you have a device outside which transfers heat from the cold outside and moves it to the hot interior of your house. And of course, that's the opposite way that heat flows in nature. So to get it to flow that way, we have to do work. So the emphasis for a refrigerator is on the heat transfer to the hot place. For heat pump is on the heat transfer to the hot place. For refrigerator, the emphasis is on the heat transfer from the cold place. So the benefit for refrigerator was Q cold or Q dot cold. For a heat pump, the emphasis is on the heat transfer to the hot place. That's the benefit. So the coefficient of performance for a heat pump is defined as Q hot divided by the work required. Benefit is the transfer of heat to the hot place. Of course, you have to do work to get heat to flow from cold to hot. And of course, on a continuous basis, we have Q dot hot divided by W dot. Okay, so this is the definition of coefficient of performance for a heat pump. It operates exactly the same as the refrigerator. It's the same device, but the emphasis is on the heat transfer to the hot place versus heat transfer from the cold place. In the refrigerator inside your house, you're not really interested in the heat rejected into your kitchen. You're really interested in the heat transfer from the icebox or the interior of the refrigerator. For the heat pump in your house, you're not really interested in the heat transferred from the cold outside. What you're really interested in is the heat transfer into your house to keep your house warm. So for the refrigerator and the heat pump, the devices are the same, but the benefits are different. In the case of the refrigerator, the benefit is the heat transfer from the cold place. And for the heat pump, the benefit is the heat transfer to the hot place. Same device, slightly different expressions for coefficients of performance. Let's do an example. Let's say we have, oh, is it a heat pump or refrigerator? Let me have a look here. Let's do both. Let's say we have a refrigerator. Let's say we have a device, a cyclic device that can operate either as a refrigerator or a heat pump. So, example. We have a heat pump or refrigerator. Heat pump or refrigerator. And let me draw a sketch for you so you can see some of these quantities that I'm going to be indicating here. Sketch or schematic. So we have a cyclic device. Let's say we have a hot place and we have a cold place. T hot and T cold are 24 and negative 6 degrees C. So T hot is 24 degrees C. T cold is negative 6 degrees C. This is probably a refrigerator we're talking about. Negative 6 degrees C is probably the freezer. The hot place is probably the interior of the kitchen. And this device is a refrigerator. Let's start off with the refrigerator. It works in a cycle, and it pulls in a certain amount of heat, Q cold, and receives a certain amount of work, W. Now, Q dot and W dot. What are these heat transfers or rate of heat transfers and works? The work input or power input, W dot is equal to 500 watts. The heat transfer from the cold place, Q dot cold, is 75 kilojoules per minute. 75 kilojoules per minute. What are we supposed to find? Let's find the coefficient of performance for the refrigerator. Let's do that first. A, COP for the refrigerator. If we treat this as a refrigerator, what's its coefficient of performance? Okay? So, received a certain amount of heat from the cold place, 75 kilojoules per minute. To move the heat from the cold place to the hot place, W dot is 500 watts. Okay, so that's the picture right there, all right? And this thing, we're going to treat it as a refrigerator and calculate its coefficient of performance. All right, let's go here to the analysis. Remember, for a refrigerator here, the coefficient of performance for a refrigerator, the benefit over the cost, is the heat transfer from the cold place divided by the work done to move the heat. Analysis. So COP for refrigerator, the benefit over the cost. For a refrigerator, we're interested in the heat transfer from the cold place divided by the work required to power the refrigerator. We have the work and the heat Let's see here. Q dot cold is 75 kilojoules per minute. And then W dot is 500 watts. Okay, the units are all screwed up here. Let's convert everything into watts. Let's see here. There are 1,000 joules per kilojoule. Okay, so that's going to get rid of the kilojoule. And there is, for every 1 minute, there's 60 seconds. The minutes will cancel out, and I'll get joule per second, which is a watt. Okay, let's see here. So 75, we have 1,000 divided by 60, and that's going to have a unit of a joule per second, which is a watt. And then we have 500 watts here, so that's a watt. So the watts cancel out. COP is dimensionless. COP is dimensionless. An energy, a power over a power, an energy over an energy. COP and efficiency should be dimensionless. Let's see here. So we have 75 times 1,000 divided by 60. And then I'm going to divide that by 500. Oops, hold on a second. 75 times 1,000 divided by 60. And then we're going to divide that by 500. 2.5. So COP, if we treat this as a refrigerator, is equal to 2.5. That means for every unit of heat transferred from the cold place, correction, every 2.5 units of heat transferred from the cold place, it takes 1 unit of work or power to transfer that heat from the cold place to the hot place. Okay? What if instead we were going to treat this as a heat pump? So let's say this thing is now, we're now told it's a heat pump, not a refrigerator. So part B, let's say it's COP and this is a heat pump, not a refrigerator. Remember, a heat pump and a refrigerator are exactly the same device. It's just the benefit is different. For a refrigerator, the benefit is Q cold or Q dot cold. For a heat pump, the benefit is Q dot hot or Q hot. Okay? It just changes the numerator of the COP. So let's say we're interested in this thing as a heat pump and we want to calculate its coefficient of performance. Well, let's go back here. And now we're going to deal with this thing as a heat pump instead of a refrigerator. Heat pump. So that's going to be Q dot hot over the power input. Okay, that's the cost. The power input is the cost. Q dot hot is the benefit. Now, unfortunately, in the problem, we don't have Q dot hot. I have Q dot cold, but I don't have Q dot hot. How are we going to get the high temperature, the heat transfer to the high temperature place? Well, let's surround now this thing is a heat pump, so I'm going to get rid of this. Same device, different emphasis. Heat pump. I'm going to surround the heat pump by a control volume and I'm going to apply the energy balance. What kind of balance should we apply? Probably rate based. We have all sorts of rates here. These are powers. So let's apply the energy balance rate based for our heat pump. So let's go over here and let's apply E balance to our heat pump. So we have our hot place, we have our cold place, We have our heat pump working in a cycle. Heat pump working in a cycle, which moves heat from a cold place to a hot place by the application of work. Okay, so let's apply the energy balance to our heat pump. Q dot minus W dot is equal to the time rate of change of energy. Okay, dE dt, and this is for our heat pump. No change in any property over the cycle. No change with respect to time. So this is a cyclic device. Cyclic device, so dE dt is equal to 0. The work, okay, there's our W dot. The heat transfer in, heat transfer, net heat transfer in. This is the total heat transfer into the heat pump. I got heat transfer from 2 different locations, in and out of 2 different locations. I have the heat transfer from the cold place, that's going in. So Q dot cold, that's being transferred in. And I have Q dot out, which is the Q dot hot. Q dot hot. Negative sign in front of the Q dot hot because that is flowing out of the device. Plus sign in front of the Q dot cold because it's flowing into the device. Remember, the Q dot in the energy balance is in or to the device positive. Okay, let's write what I have left over. Q dot cold minus Q dot hot minus W dot. Actually, we have to be a little bit careful here. This W dot in the energy balance, that's done by the system, hence the negative sign. This is done on the system. This W dot is done on the system. So I am going to actually put in a negative W dot here because this is on the system. On the system. The negative signs cancel out, and I get a plus W dot. And all that sums to 0. So remember, this negative sign here is because it is on system. Negative times a negative will cancel and give me a positive. Okay, I know the W dot, but I don't know Q dot hot. Let me solve for Q dot hot by the energy balance. Let's see here. Let me pull the Q dot hot over on the right-hand side and flip the whole equation. And I get Q dot hot equals Q dot cold plus W dot. Okay. So the heat transfer to the hot place is equal to the sum of the heat transfer from the cold place and the work done to push the heat from hot to cold. These two added together is equal to the heat transfer to the hot place. Okay, so Q dot hot is Q dot cold plus W dot. And then in the denominator, I have W dot. So that's going to be equal to Q dot cold over W dot plus 1. Q dot over W dot plus 1. Let's see here. If you recall, this guy here is just the coefficient of performance for the refrigerator. We've already calculated that. Coefficient of performance for the refrigerator, Q dot cold divided by W dot. And we already calculated that is 2.5. Add a 1 to it, and I get 3.5. So the COP, if we treat this as a heat pump and not a refrigerator, is equal to 3.5. Okay? So if you call this thing a refrigerator, then the coefficient of performance is 2.5. If you want to treat it as a heat pump, it's equal to 3.5, okay? Same device, different benefit, therefore different efficiency, i.e. coefficient of performance. Okay, let's take a pause here. All right, so let's move on to chapter 5. We finished with the energy balance. So let me point out something kind of strange before we move on, kind of whet your appetite. All the problems that we previously did up to this point in the class, all the example problems we did using the energy balance or any problems in general, I could have done those problems in reverse order. So every example we did where we went from process 1 to 2, I could have easily done the problem where we're going from state 2 to 1. So process 2 to 1, I could have done in the reverse, and we could have done calculations for the process 2 to 1. So I could have reversed every example problem in this course. The sign on the change in properties would flip, so the positives would become a negative and vice versa. The heat transfer and the works, the signs would flip. And I could have proceeded and done the problems in the reverse order. And again, all that would change would be the signs on the results. Okay, so the energy balance doesn't appear to care about which direction the process goes in, whether it's from state 1 to state 2 or from state 2 to state 1. The energy balance doesn't really care. Now, this is kind of a problem when we take into account or look at 3 different kinds of processes. Let's look at 3 different kinds of processes here. The first one is heat transfer across a finite difference. Finite temperature difference. Heat transfer across a delta T. So let's look at heat transfer across some temperature difference delta T. So we have a hot bar at a temperature T plus delta T, and we have a cold bar at a temperature T. Temperature T, a little bit warmer or hotter, T plus delta T. Okay, so that's state 1. We have the hot bar, and we have the cold bar. Temperature T, T plus delta T. Delta T is some positive temperature difference. Now we know from experience that if we leave these 2 bars in contact with each other, the temperatures will even out. Heat will get transferred from the hot to the cold bar until the temperatures are the same. So we do know that over time, if we wait long enough, we'll end up with a temperature T2, and they will both be the same, okay, for the hot bar and the cold bar. So this is state 2. Now, the energy balance doesn't care which direction the process occurs. I can go from state 1 to state 2, which we're all familiar with in everyday life, or the process could go from state 2 to state 1, as far as the energy balance is concerned. The energy balance doesn't care which direction the process goes. But think about it. Has anybody ever seen 2 bars touching each other? Let's assume there's no microwaves around, there's no heat pump or heat engine transferring heat. These are just two isolated bars. Isolated bars at some location. You've never seen two bars sitting there or a single bar. You've never seen a single bar at some temperature all of a sudden spontaneously get hot on one end and cold on the other. Not without the application of work from the outside or an application of heat transfer from the outside. You've never seen two isolated bars or a single bar isolated, no work, no heat transfer from the outside. You've never seen one side get hot and the other side magically get cold. That's magic. So in nature, we've always seen this process go from state 1 to state 2, never the other way around. Okay? To go from 2 to 1, well, that's magic. That's magic, okay? So processes involving heat transfer over a finite temperature difference, delta T, are unidirectional in nature. They only occur from state 1 to state 2. Heat only spontaneously, naturally flows from hot to cold, not the other way around. Okay? So, processes which occur in nature naturally are, or if you like, spontaneous. Spontaneous or natural processes. Spontaneous or natural processes. First one is heat transfer across a delta T where delta T is not equal to 0, okay? Maybe I should be a little bit more precise here. Delta T has to be greater than 0, okay? So heat naturally flows from hot to cold across a delta T. This is called a spontaneous or natural process. It's a process that we see in nature. We always see heat flowing from hot to cold and the system going from state 1 to state 2. Okay. Let's look at another natural or spontaneous process. What's another natural or spontaneous process? Processes involving friction. Involving friction. Remember the first day of class, we had a table and a moving object. So we had a table and some moving object, OBJ, okay? So velocity 1 is greater than 0. And because there's a little bit of friction going on between the object and the table, so we got an object sliding across the table, there's friction. If we wait long enough, the object will stop. Okay, so the object ends up over here, and velocity 2 is equal to 0. So this is state 2. And of course, where does the energy go? Where does the kinetic energy of the object go? It goes into heating up the table object system. So the table and the object had a temperature T1, and the table and the object had a temperature T2. And in this case, T2 is greater than T1. The kinetic energy of the object got converted into internal energy and heated up the table object system. So in nature, if we don't do any work on the system, if we don't go in and actually move the object, we just isolate it. If we just isolate it and let this object slide across the table, over time it will naturally slow down. So in nature, we always see this situation evolve from state 1 to state 2. Okay? So given the choice between going from state 1 to state 2 or state 2 to state 1, in nature, friction always converts mechanical energy, kinetic energy into internal energy. Okay? So in nature, we go from state 1 to state 2. Now, if we somehow went from state 1 to state 1, that would be called, again, magic. Magic. Doesn't happen in nature. Doesn't happen in nature. That would be magic if all of a sudden an object at rest, all of a sudden without any external interference, all of a sudden started moving. Stationary object magically started moving. That would be, again, magic. Nature, moving objects always slow down and stop due to friction. Okay? So spontaneous natural processes. Another one is processes involving friction. They always go from state 1 to state 2. What I mean by that is we start off with the table. And we always go to the object slowing down and stopping. Okay? So processes involving friction have a natural direction in the real world, and that's for friction to convert mechanical into internal energy. Okay? There's a third kind of natural or spontaneous process, and that is unrestrained expansion of a gas. Seems like kind of a mouthful. Unrestrained expansion of a gas. So heat transfer across a finite temperature difference, processes involving friction, those all go in one direction in the real world. Another one that goes in one direction, the process that goes in one direction, is unrestrained expansion, unrestrained expansion. What do I mean by unrestrained expansion? Let's say, this is going to be kind of weird, but just bear with me. Let's say we have two tanks that are connected together. So I have a tank of some kind of gas here, and I have a vacuum down here. Okay? So this is state 1. Two tanks that are connected together by a small connection. Gas in the top, vacuum in the bottom. What's going to happen? If I isolate this system, I don't do any work on it, I don't transfer any heat, I just leave it alone. What is going to happen? Well, clearly, the gas is going to rush down into the bottom tank until the pressures are equalized in the bottom and the top. So in nature, the gas will expand to fill the vacuum. So I'll have a gas up here, and I'll have a gas up here, and the pressures will be equalized, okay? So up here, I have P gas 1, pressure 0 down here. And in state 2, I will have P gas 2, P gas 2. Pressure is the same in the bottom and the top tanks. So in nature, this process always goes from 1 to 2. So in nature, we always see this situation occur from state 1 to state 2. We never see a gas or some kind of material, could be a liquid, I suppose, too. We never see a material, let's stick with a gas this time, distributed evenly throughout some kind of space, all of a sudden magically rush to one side of the container or fill a sub-area of the container. We never see a gas spontaneously move to form a vacuum. Okay, we always see gas expand into a vacuum. Okay? So unrestrained, there's no restriction, there's no separation between these two spaces. Unrestrained expansion occurs spontaneously in nature. Unrestrained expansion always occurs from state 1 to state 2. Always occurs from state 1 to state 2, never the opposite. We went from 2 to 1 without doing any work or anything. That would be magic. That'd be magic again, okay? We're not dealing with magic, we're dealing with the real world. So we have 3 kinds of processes. Heat transfer across a finite temperature difference always occurs with heat moving spontaneously from hot to cold. Processes that involve friction always convert mechanical into internal energy or heat. Unrestrained expansion, well, gases always expand to fill a vacuum spontaneously, okay? What I mean by spontaneous here is without any external interference. I could do work to pump gas out of the lower tank into the upper tank. I could connect a pump or a compressor to that system and suck all the gas out from the bottom, but I'd have to do work to do that. I'm not talking about work. There's no W here, okay? Spontaneous process in nature. Heat transfer across a finite delta T, processes involving friction and unrestrained expansions, okay? Okay, let's look at a little handout that I have posted here. Let's go over some terminology. Oops. I'm going to change the view here. Hold on a second. Oops. View. So let's go over a handout here I have posted. So I posted on Canvas terminology, relevant terminology that will be applicable to the second law of thermodynamics. This stuff here, I hope, is whetting your appetite for some of these concepts. The first one we can look at here, let's go to the second page. Spontaneous processing. Let's read this over. You can think about spontaneous means occur in one direction only in nature. That's what the term irreversible means. That's what the term irreversible. Spontaneous or irreversible processes. Processes which in nature move a system to from an initial to a final state, but not in the reverse. So in nature, a spontaneous or irreversible process occurs in one direction only. Another version of this, let's read the second definition. An isolated system moving from an initial state A to a final state B is said to undergo a spontaneous process A to B if the reverse process B to A does not naturally occur. Okay, so these are word definitions of the pictures that we just drew a moment ago for a spontaneous process. Another way of describing a spontaneous process is referring to the arrow of time, the direction of time. The three processes that we just talked about: heat transfer across a finite delta T, unrestrained expansion, process involving friction. They occur in one direction only over time in the real world. So right here where you got this nice big space, why don't you draw the three processes we just listed? Heat transfer across a finite delta T, process involving friction, and unrestrained expansion. Draw those situations. Start with the original state 1 and go to state 2. Draw those three situations and you will have a pictorial representation of three spontaneous irreversible processes. So take a moment, pause the video here, pause the video, and draw in the three processes. Unrestrained expansion, process involving friction, in this case, a object moving across a table, and then have the heat transfer, which I just erased, from hot to cold. Those are all spontaneous or irreversible processes. Sketch those in the space provided in your nomenclature handout. So sketch those in right here. Okay, so now you have one part of the handout filled out. Each one of these big spaces here, blank spaces, we're going to be putting pictures in. Okay? So now let's go to the very top of the first page of the relevant terminology. Let's define a brand new term. We've talked about irreversible or spontaneous processes. Let's talk about reservoirs. Again, what are the three spontaneous or irreversible processes we looked at? Well, heat transfer across a finite temperature difference, unrestrained expansion of a gas, and processes involving friction. Those are three irreversible or spontaneous processes. They occur in one direction only in nature. They give us a clue as to the arrow or the direction of time. Let's define a reservoir, brand new topic. Reservoir. Okay, what's a reservoir? Well, let's look at the definition here. Reservoir, a body or system of large enough extent such that temperature is equal to a constant for any finite heat interaction. What do I mean by heat interaction? I mean a heat transfer into or out of the system. So a reservoir. So I add heat to this system called a reservoir. Okay? So this is state 1. And initially this reservoir has a temperature T1. So I add a certain amount of heat and I end up at state 2. T2 is approximately equal to T1. It's constant. If I have a reservoir. What that simply means is the reservoir is a huge system. It's so big that for any reasonable heat transfer, temperature is approximately constant. When you transfer heat to a system, the internal energy, let's say a closed system, the internal energy goes up. Well, this thing is so massive. There's so much mass in this reservoir that delta T from 1 to 2 for the reservoir is approximately equal to 0. So T delta T from 1 to 2 is approximately equal to 0. In other words, T is constant. T is equal to a constant for the reservoir. Okay, so draw these pictures. Draw these pictures illustrating the concept of a reservoir. A large system such that for any finite heat transfer or any reasonable heat transfer, temperature is approximately equal to a constant or equal to a constant as far as we're concerned. Okay? So that is a reservoir. Put that picture of a system, a big system, so big, any finite heat transfer doesn't change the temperature. Cyclic process. We've already talked about a cyclic process. Well, let's go back here and again remind ourselves what a cyclic process is. So what's a cyclic process? We have a system. What's a cyclic process? We have a system that moves along some process or path. Cyclic process. So we have a property plot for some system. So we have property 1, property 2. And this system starts off at some initial state A, or 1, whatever, moves through a bunch of intermediate states. So here's B, here's C. It just keeps moving around, and then it returns back to its original state A. So change in any property over the process. The cyclic process, change in any property over the cycle or the cyclic process is going to be equal to 0, okay? So sketch in this property plot and indicate some kind of a cycle or a cyclic process. And remember, the change in any property, internal energy, temperature, pressure, any property is equal to 0 over a cyclic process. Okay, that's the picture that should be going in the white space under cyclic process. Okay. Efficiency. We actually don't have a picture for this one, but we know about what efficiency is. Efficiency is a benefit over a cost. We just did a problem involving a refrigerator and a heat pump. There's also heat engines. And they have their own definitions for coefficient of performance or efficiency. Okay? The universe. What is the universe? Well, the universe is everything. What's the universe? The universe is everything. We have the system. We have the universe, which is everything. So here's the universe. There's the universe right there. It's everything. everything. And of course, in the universe, we have our system. So maybe we have our system. There's our system right there. The universe is everything. There's our system. It's within the universe. It's just a little confined region or mass within our universe. And then everything that is outside the system contained within the universe is called the environment. So the environment is the universe minus the system. The universe is everything. The system is here within the universe, a small part of the universe. What is left over is the environment. It's what's outside the system. The environment is outside the system. It's the universe minus the system. Okay? So you have, I think, a couple here you can fill out at this point. The universe, the environment. Okay, so draw the same sketch here. Put in your system. Everything outside of the system is the environment. So the environment is external to the system. Okay? Okay, so we've talked about reservoirs, cyclic processes, the universe, the environment now, spontaneous, irreversible processes. By the way, what's this about? Reversible processing. An isolated system moving from an initial state A to B is said to undergo a reversible process if the reverse process B to A can occur naturally or spontaneously. What do I want you to put down here? Just write processes that don't involve friction, unrestrained expansion, or heat transfer across a finite delta T. In other words, processes that don't have any irreversibilities are reversible. Okay, so for the bottom one, we can have a system moving from an initial to a final state, and it can go in any direction. So here we have our system. It's going from state 1 to state 2. This process can go in either direction, state 1 to 2 or 2 to 1. Notice the double arrow sign. It can go in either direction. So 1 to 2 and 2 to 1 will occur or may occur if no irreversibilities or irreversible processes present. No irreversible processes present. What do I mean by that? No heat transfer across a delta T, a finite delta T. Unrestrained expansion. Expansion. And no friction. So a process can occur in any direction, 1 to 2 or 2 to 1 for some system. an isolated system, if the process doesn't involve heat transfer across some finite temperature difference, unrestrained expansion, or friction. Then the process is what's called reversible. I can go 2 to 1, 1 to 2. Either one may occur technically. Either one may technically occur. And these processes that can go in any direction must not have heat transfer across a finite temperature difference, unrestrained expansion, or must not include friction. Okay? All right, ladies and gentlemen, let's take a pause there.